Hi. So, an introduction to quantum mechanics and why we're studying the things that we're studying. So, I'm going to give you a brief overview of the various atomic theories or the evolution of atomic theory that got us to basically where we're going to start in learning quantum mechanics. So, 1803. Actually, let's go back to 3000 or 2000 BC, 1000 BCE. I'm not quite sure. Probably 100 BCE of the Common Era. Anyway, so Democritus was the first, he's a Greek philosopher who said, you know what, I bet stuff, the ultimate question, what is stuff, is made of tiny, tiny little particles. Now, he thought that they were actually made of the Platonic solids and things that had certain Platonic solid character, like the little, I think it's the tetrahedron has little sharp points. And so if it hurt or was like fire, it would be made of little points. And that's why it was painful. Not quite right, but the idea of atoms or atomus, which means indivisible in Greek, held. So John Dalton took up that theory in 1803. He was a Quaker who was recognized for his work on this idea that so atoms are, or stuff is made of atoms, and atoms are indivisible, these teeny tiny little particles. We now know that that's not true. It was later discovered that protons, neutrons, and electrons exist, not in this order. It was actually electrons were discovered first, followed by the protons, and then followed by the neutrons. And so you had this development of evidence or observation that didn't match theory. And so you had to continue to go back to your theory. Now, notice I'm in 1803 with John Dalton. J.J. Thomson comes around. He discovers the electron in 1904, 100-year difference. And in between that time, guess what was developed? So the periodic table was actually developed across this span of time, starting really with Wolfgang Dobereiner, who recognized that there were these things called triads, lithium, sodium, potassium being a famous triad, and there was some sort of connection between the elements. And then you had Antoine Lavoisier, who listed all the elements and recognized that there might be some connection between them. And it goes further still. And then Mendeleev and Lothar Meyer, two of the most prominent scientists who figured out the periodic table, did all of this not knowing atomic theory. In fact, Lothar Meyer agreed with atomic theory. He was more of a physicist by training. Mendeleev didn't. He was a chemist through and through, and he's like, this atomic theory is dumb, because he thought that elements had a almost metaphysical property to them. They represented the essence of a compound. So if you had a gold element, it was pure gold, and it wasn't necessarily indivisible into anything but gold. And so it couldn't have been indivisible because it was just, it was a pure substance. So a lot of work could be done without knowing any of this information. But as observation and techniques got better and better, we were able to probe into materials or matter deeper and deeper. And these discoveries they overlay with the same development in understanding light. And so, as you'll see, again, this is a quantum mechanics and spectroscopy course. Light, the electromagnetic spectrum, which is the video you'll see next, breaks light down into these various wavelengths, and we can probe different parts of the atom by these various wavelengths. And so as that understanding was developing, we were able to understand the atom that much better. So we get to 1904, J.J. Thomson discovers the electron, and he proposes the plum pudding model. He was British, so plum pudding was all the rage. I prefer the chocolate chip cookie model because chocolate chip cookies are just so delicious. So he discovered the electron. Fun fact, George Thomson, his son, discovered that it was a wave. He discovered it was a particle, so that's kind of cool. Share the Nobel. Family dinners must have been fun. And so J.J. Thomson said that the atom is charged as a positive charge. Oops. So he has, good God, here we go. He's got this big positive here, and then smeared around that is the negative. And it's not just that the positive is located here. Everything, let me grab another color. Everything that I'm putting in purple is positively charged. It would be like a chocolate chip cookie. So the cookie part is the purple, that's the positive charge. And then the chocolate chip chips themselves, the little bits, are the negative charges. And so they're scattered throughout. And so all the mass is distributed throughout the atom. Now, we now know this is wrong because there's no nucleus. So this gets us to 1904. Now we're going to go to 1911 and introduce to Ernest Rutherford. Okay, so Ernest Rutherford, 1911, he introduces the nucleus model, which has the nucleus as a dense core. And there's a problem with it because it doesn't help us understand why electrons don't spin into the center. But let's talk about how he made this discovery. And I shouldn't say he made this discovery. He had a team of researchers. He had 2 graduate students working on this project. I think it's Ernst Martzen, and then I can't remember, Hans Geiger. I think it's Hans, but Geiger, the inventor of the Geiger counter, for the work that he did here. So the idea behind the Rutherford's experiment is called the gold foil experiment. So you have gold foil, and I'm going to make this obviously not to scale. So gold is a wonderful element that it can be smashed into these very fine sheets that are almost monolayer thick, single layer atoms. And so we know that, so gold, AU, and if you look to your periodic table, which you should always have handy, 79. And so it's got 79 protons, 79 neutrons, depending on the isotope, right in the center. So what they did, was they took an alpha particle, which is a helium nucleus. Think about what a helium nucleus is. 2 protons and 2 neutrons. And they shot it at this gold foil with a detector here. And it's really kind of funny. So a Geiger counter is something that picks up radioactive decay. So anytime you go, is it radioactive, and you have a little thing and it goes click, 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 when you put it close to something that's radioactive and then you take it away and the clicks become less. Those clicks are sensing basically particles that are being radioactively emitted. And so the way that Geiger figured out that you could do this was they had to turn out the lights, and on this plate, it was a photographic plate, there would be these little sparks every time an alpha particle would hit. And so just like when you want to go out and see the stars, you got to, acclimate your eyes. And so Geiger would sit in the dark for like a while, and then, he'd acclimate, and, you couldn't open the door because he'd be like, oh my gosh, I'm blind. But so he's watching these little flashes. Anyway, and so years later, of course, he was able, and he would see it, that there was a detection. Anyway, so he developed the technology for the Geiger counter. Go team. Okay, so in a mark of brilliance, or just being honorary in terms of science, Rutherford really liked to go out on these extreme ideas. And so he's like, and he may have just been messing with his graduate students. Who knows? Advisors do that. But he's like, I know. Why don't, well, actually, let's go back for a second. So the plum pudding model, all of the mass is evenly distributed throughout. So if you shine or shoot alpha particles, they should not necessarily go to there should be some sort of deflection, but the majority of them came straight through. Think about why that is. The nucleus is tiny, so tiny. Even 79 of gold is teeny, teeny, tiny. Let's give it some perspective. If you were to take all of Lambeau Field, okay, so here's Lambeau Field, football stadium. You take a golf ball. I don't have a golf ball. Go team, but I have a marker. We're going to put this marker right in the center of the 50-yard line, okay? That's the nucleus. The electrons on the outside, and this is just of a hydrogen atom, are all the way up to the very top of the real cheap seats at the top of the bleachers, okay? So you've got this very, very dense core. All of the mass, for the most part, is right here. And then up, 50-yard line golf ball, and then all the way up at the top is where the electrons could be. I say could be because we're getting to the actual model of quantum mechanics. Anyway, and so if you were to shoot alpha particles through this space, 1000% of them are going to go straight through. Well, this negates the plum pudding model. Like, well, that's weird. Why does it happen that way? And so in a stroke of brilliance, and or just really messing with his grad students, who I don't think really liked this project anyway, it was like, why don't you put the detector behind the alpha, or the gold foil, which meant put the detector back here. Go team. And what do you know? There was a detection. How was there a detection? One of the alpha particles hit the nucleus and was deflected backwards. And of course, they didn't believe it. They were like, what the hell? something's wrong, did it again. And granted, majority of them are going to go straight through. Every once in a while, and it's that once in a while, you're going to have this deflection. And so Rutherford was quoted as saying, and you'll read this in the Bohr biography, as saying that it is if you hit is if you shot a shell, so a bullet, at a tissue paper and it came back, it ricocheted and came back and hit you. He was so excited, he was crying. He's like, oh my God, this is amazing. And thus we now know there's something very, very dense, enough that an alpha particle can interact with it and its mass can transfer and bounce it back, which meant that the majority of the mass was in that center. So this was the model. Well, this model. So you had this positive center, very, very small positive center, and the electrons existed outside. Okay, but there's a problem here. If this is the model, what's keeping the electrons, negative charge, from like smashing back into the positive charged nucleus? We don't know. Well, I mean, we do know now. But at the time, 1911, they didn't know. And this is where Niels Bohr comes in and he says, I have an idea. Here's the Bohr model. Go team. Pause. And now let's go to 1913 and Niels Bohr. Okay, so now we're in 1913, Niels Bohr, and Niels Bohr did not work alone. He was probably one of the most brilliant scientists of our time, or of humanity, in all honesty. He was good friends with Einstein. He was friends with Schrodinger, Erwin Schrodinger, Werner Heisenberg. They were very close. And you'll learn all of this in the Bohr biography. But I think that we have a substantial amount of gratitude towards Niels Bohr for all of his work. It's unfortunate that Einstein gets all the credit for being like the most revolutionary scientist, which he was. He was incredible. However, Niels Bohr, I think, really, he's at the top of my list. So what he did was he said, okay, let's think of this as kind of a planetary model. So where you have like the proton or the nucleus that Rutherford proposed is in the center, so like the sun, and then you've got these orbits of electrons around the outside. And so this is likely the model that you think of when you were in school, when you were thinking of chemistry and you're filling your octet and orbital shells. This is wrong. This is wrong. He won the Nobel Prize for it. All of our atomic theory is based on it, but it's incorrect. It turns out that the way that the atom really is purely mathematical. And we'll get to it. We're going to spend the whole class getting to it. But what is important of this is that electrons are stable in an orbit around the nucleus. Okay. And so the other thing that he says is the angular momentum is quantized. And I'm going to make another video, the next one, that goes into what do we mean by angular momentum is quantized, because we're going to need to use the angular momentum idea when we get into developing, putting an electron around a dense nucleus and seeing how it stays. Anyway, but there's a downside to this model. And his model only held, so 1913, so it was about 1936 or 1926, 1930 or so when quantum mechanics really took hold. So his model was really only about 10, 15 years before it broke down. But still, it's what we build on, and especially what we conceptualize. This is the last thing we can really conceptualize before we move into Adrift in a Sea of Mathematics, that you'll read in the Bohr biography. But what's the problem here? So the problem is that things that have, so let's take this electron right here. Okay, so it's accelerating, and acceleration is, so acceleration equals d squared x dx squared. Oops, sorry, dt squared, sorry. Okay, so this is the second derivative of position, which is also the time derivative of the time derivative of position, where this is its velocity. Okay, now velocity is both a magnitude and a direction. It's a vector. And so you've got a direction associated with this velocity. All right, but if you have a change in the direction, you have a change in the velocity. Okay, so this is changing its direction. So if it's here, the velocity is essentially the tangent, and so it's continuing to change. Well, as you change here, you've got a change in the angular momentum. And if you change the angular momentum as it goes around, then, and the momentum being, the velocity times its mass, but then you've got an angle associated with this. So the angular velocity or the angular momentum. So what's going to happen is, go team. Sorry, the nanny texted and then I kept talking and I thought I had to push the record button. And it turns out I hadn't, so I just kept talking. So I'm going to kind of start over. So we have talked about how you have this charged nucleus and the electrons are around the outside, and why don't they, when they orbit, why don't they lose energy and spiral into the center? Okay, so it was known that their angular momentum, so you've got so V is the velocity that they've got. It's a vector. You've got the mass of the electron, and then you've got, oh, my bad. That should be R. So this is angular momentum. So VMR, and so the R is the radius here. Okay, and so you're going to have it sweep across the angle, 2 pi around. And so it was, so since this mass is charged, it's got a negative sign, it was known that as electrons move, charges move, they're going to emit radiation. If it emits radiation, that means it's losing energy. Okay, so if it's losing energy and it's going this direction and then, moving that way, then you're going to have basically, as it turns the corner, you're going to continue to lose energy, lose energy, lose energy, lose energy. And then it's going to just continue to spiral as it maintains that angular momentum, but it's going to continue to lose that charge or lose that energy. Sorry, it's going to lose angular momentum in terms of losing that energy. And so it can't contain that angular momentum. So that's an issue. And so Niels Bohr said, well, what if, I have an idea, what if it's centrifugal force here? So the force pulling this electron here is equal to the force exerted by its, basically, is it spinning around, that force exerted this way is proportional to the force exerted that way. So it's stable, okay? And so it can maintain this orbit. So that conservation of angular momentum occurs. And so because it's not, basically because it's stable, it's going to stay in its orbit. Go team. Dang it, hang on, sorry. Cool, sorry. Nanny's, I told her to stop texting. Anyway, so this is a problem. And it worked fine for hydrogen atom. And it turns out that the Bohr model works beautifully for really light atoms in terms of a small nucleus. And they actually match this to atomic spectra, which we will do. But as you get to heavier atoms like gold, it breaks down pretty quickly. Or not even like gold, like lithium. So it breaks down pretty quickly. And so what is the actual model of the atom? In comes Erwin Schrödinger and Werner Heisenberg, who worked with Niels Bohr at the Niels Bohr Copenhagen Institute, or the Bohr Institute in Copenhagen, where Bohr worked with them, and Wolfgang Pauli, Paul Dirac, all of these characters you'll meet in the Bohr biography. But what he did was he created a space such that all these scientists could come together. And Niels Bohr was adamant that his model was wrong. They got data that said, yep, it doesn't match observation. Your theory must be wrong. And he's like, cool, it's wrong. Let's find a new one. And so that's where quantum mechanics comes in. Okay. So Erwin Schrödinger and Werner Heisenberg. So Schrödinger developed what's called wave mechanics. Heisenberg developed matrix mechanics. They have their pros and cons. But the idea is that you have this internucleus, and on the outside, you have some sort of, and I don't even want to draw a circle because that would tell you that there's a boundary. So I'm going to do this. So I'm going to do really... Oops. Actually, that's kind of nice. So you see the dark line. Imagine that that's a radius. And it's really dense right here, and then it gets lighter and lighter and lighter and lighter and lighter and lighter, and then it just disappears as we go. So there is a probability that the electron, so this would be for the hydrogen atom, that the electron exists somewhere in this dense core, and then it gets kind of higher or lower probability, and then the probability disappears. So it's a probabilistic model that's mathematically this. Psi squared d tau is equal to 1 if you integrate over all space. We are going to dive into what this means. This is the current model of the atom, or at least it's a pretty good one. There are a couple others. But this is what we're going to spend all of our time building up and then using to look at spectroscopy. And so let's see what I have written. So it shows electrons don't move around a central core. They are waves, that they are in a standing wave around the nucleus. There is a probability associated with their location, and there's an associated uncertainty with their location. It's dictated by the Heisenberg uncertainty principle. And again, we haven't yet broken this. We haven't found reasons that this doesn't hold. Unlike some of the other models where we saw data or observations that broke down that current model. So this is quantum mechanics. Go team. This is what we're going to be studying. It's a probabilistic mathematical representation of how electrons respond to measurement. Go team. Okay, cool. The next video is going to introduce you to the Bohr model, so you have at least more foundation mathematically of what was built on, or how quantum mechanics was built. And then we're going to dive into quantum. Go team. Bye.